In this video, we're going to another tremendous application of vector spaces, and that's for conic sections and rotations. I just want to start with a little history of me. The very first hyperbola that I ever saw was when I was in 8th grade. My teacher, Mr. Dubinsky, he wrote the equation xy equals 12, and he made us realize that, well, if x is 3, y is 4. If x is 4, y is 3. If x is 6, y is 2. If x is 12, y is 1. If x is 24, y is going to be 1/2, and so on and so forth. And similarly, the other way around. And basically, that this graph is going to be asymptotic to the x-axis and asymptotic to the y-axis. And just like you have two positive numbers, you're going to have two negative numbers. Anyway, this is a hyperbola, and that was really cool. Then I got to algebra, high school, whatever. And then I got to algebra, and I noticed that all the hyperbolas never looked like this. All the hyperbolas were like more like side to side or top bottom. You know what I'm saying? In other words, let's see. In other words, they look kind of like this. Oops! Oh, I just passed it. Like these guys right here. That's a side to side. That's a top bottom. You don't see them like on that kind of like diagonal, like Mr. Dubinsky's hyperbola. And the answer was in the equation itself. The answer is in the xy term. That the thing that makes a conic section sort of tilt is the xy term. And if there is no xy term, then it's going to be straight. The axis. Another way of saying is that the axis will be parallel to the coordinate axes. And by the way, the fancy word for tilting or putting on an angle or diagonal, the fancy word for that is oblique. Anyway, here's some standard forms of conic sections. That's a circle, a minus h squared, y minus k equals r squared. That's a circle with radius r, and the center is h comma k. Another type is the ellipse. X minus h squared over a squared, y minus k squared over b squared equals 1. And so on and so forth. You get the minor axis, major axis, all kind of cool stuff. And then of course, this is our typical hyperbola. These are the equations for it. You've seen this already in algebra, in regular old algebra. And then of course you have the parabola. This is the famous y squared, x squared equals 4py. P is being the focus, and p is the distance. P, not the focus actually, but p is the distance from the vertex to the focus. When the focus is higher than the vertex, p is going to be a positive number because you're going up. If p is a negative number, that means the parabola opens down. And this is stuff you did or should have done in high school or intermediate algebra, or whatever, college algebra, I don't know, somewhere along the line. I'm sure you've done this stuff. And here we have just some basic, here if you have a y and you have an x squared, and if you rewrite it this way, you could rewrite this as x minus 1 squared equals 4 times negative 1 times y minus 1. Negative 1 is by p, and since p is negative, it means it's going to go downward. So the vertex, of course, is 1, 1, and p is straight down 1 from there, which means the focus point is going to be 1, 0, because you're just going down 1. And here's the standard form. Here we have an equation. Notice there's no xy term here. We're just going to complete the squares, blah, 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 and we get anybody know what this is called? This is called a ellipse. And ellipse is when you can't see the sun or the moon. I'm just kidding. That was a joke. Anyway, so here's the parabola we were just looking at. We were just graphing, and here's the ellipse we were just graphing. Anyways, these examples. Anyways, when these examples I just gave a minute ago were there was no xy term in the equations, and that's why again they were like parallel. The axes were parallel to the xy axis. Sometimes it's if you have an xy term, it's going to be you're going to be at that oblique angle, and sometimes it's helpful to rotate the standard axes to form a new x-axis and y-axis, and the required rotation angle theta is measured that cotan of 2 theta equals a minus c over b. That's how we figured this out. And the A, B, and C are from the original equations. Where are we here? Where are those original equations? These guys right here. These are the A, B, and C that we're talking about. Let's just go back down to where we were. And okay. So this rotation, the standard basis for R2 is 1, 0, 0, 1. And that's going to be rotated to form a new basis of cosine theta, sine theta, negative sine theta, cosine theta. And that's going to represent a rotation in the positive direction of, which is counterclockwise, oh boy, I wonder if students even are going to be knowing what counterclockwise means, because nobody uses those kind of clocks anymore. Anyway, anyway, this is what it looks like. And let's look at an example. Now, suppose you want to find the coordinates of a point x comma y relative to this new basis. So you could use the transition matrix that we learned about in this section, in this chapter, and as follows. So what we want to do is we want to find the coordinates of a point x comma y in the R2 plane. But we want to find the coordinates not relative to not the standard coordinates, but we want to find the coordinates relative to the basis cosine theta comma sine theta and negative sine theta comma cosine theta. So by theorem 4.21, we write the two bases next to each other. This was in the section of change of basis section. We write the two bases next to each other, and so here's the B prime base. The basis, and here's the standard basis. We turn the left side into the identity matrix, and the right side becomes our transition matrix. And there, which means if I take cosine theta, sine theta, negative sine theta, cosine theta, multiply that by x comma xy, that's going to give me the x prime comma y prime, and that's going to give me the now, that means that x prime, just by multiplying it out, is going to equal to x cosine theta plus y sine theta, because if I just multiply this row by that column, that's what I get. And then the y prime is going to be this bottom row times that only column that there is. So it's going to be negative x sine x plus y cosine y. And that's going to be well, let's just put it into one big theorem. So if we have a general second degree equation, ax squared bxy cy squared dx ey f equals 0, this can be written in the form a prime. And a prime, but prime just means a new a, and prime just means a new x. So a prime x prime squared plus c prime y prime squared d prime x prime e prime y prime f prime equals 0. So the a prime f prime, all that stuff is just different constants, and the y prime and the x prime are these guys right here, based on what we just did. And notice that there's no xy term, there's no b, and there's no xy term. Anyway, by rotating counterclockwise to an angle theta, where theta is defined by cotan of 2 theta equals a minus c over b, the coefficients of the new equation are obtained from the substitution x equals x prime cosine theta minus y prime sine theta, and y equals x prime sine theta plus y prime sine theta. And it has a lot of applications. It has applications in satellite dishes and all kinds of cool stuff. Let's actually do a rotation of a conic section. So what we want to do now is perform a rotation of axes to eliminate the xy term in this conic right here. Now this conic, you notice there's an x squared and there's a y squared, and all that cool stuff. This is going to be It may not look it, but if you were to graph this, you can get an ellipse, but you get an oblique ellipse. We'll graph it later. Let's just do the math first. So the angle of rotation is given by cotan of 2 theta equals a minus c over b, which is 5 minus 5 over negative 6, which is 0, because that's a and that's c, so it's 5 minus 5 over b, which is negative 6, and that's 0. Now, if cotan of 2 theta equals 0, remember, cotan is cosine over sine. That's basically a way of saying that sine is 0. Well, sine of 90 is 0, which means if 2 theta equals 90, so theta equals 45, or in radians, pi over 4. That's where pi over 4 comes from. Which means that sine of pi over 4 is 1 over rad 2, and cosine of pi over 4 is also 1 over rad 2. Now we're going to make that substitution, and this is going to be x is x prime cosine theta minus y prime sine theta. But cosine theta and sine theta are both 1 over rad 2, so x is equal to 1 over rad 2 times x prime minus y prime. And doing a similar thing, we get y is equal to 1 over rad 2 times x prime plus y prime. And we take this and we put it into the original equation and crunch things up a lot. And this is what we get. Let me just move here so you can see the graph. So this is what the new equation is going to look like. And if you complete the square and put it in the standard form, you're going to get this. So again, there's an x squared term, a x squared, a y squared term, but there's no xy term. And voila, this is now. Well, actually, we're not done. So we rotated this. Now, what are the axes? I'm sorry, not the axes. What are the vertices of this rotated ellipse? So the new rotated basis is b prime is equal to 1 over rad 2, 1 over rad 2, negative 1 over rad 2, and 1 over rad 2, because that was the sine theta, cosine theta, and so on and so forth. And the coordinates of the vertices of the ellipse relative to b prime are going to be negative 5, 1, and negative 1, 1. And to find the vertices relative to the standard basis, we're going to say that x is equal to 1 over rad 2 times x prime minus y prime, and y is equal to x prime plus y prime. And if we plug in the x prime y prime that we have figured out, let's plug in the x y prime and crunch it around, we get the vertices of the ellipse are going to be negative 3 rad 2, negative 2 rad 2, negative rad 2, comma 0. Those are the vertices. And let's just see if Desmos agrees with that. So here's Desmos. Now I just typed into Desmos the initial equation. 5x squared minus 6xy plus 5y squared plus 14 rad 2x minus 2 rad 2y plus 18 equals 0. I couldn't fit the whole thing on the screen. I just plugged it in the regular, just in the regular, and here I have, this is one axis, that's the other axis. So this is the major axis, that's the minor one. And if you notice the vertex, well, 1.414, that's the square root of 2. So this is negative rad 2, comma 0. And all these numbers here, that's the center of the ellipse, by the way. All these numbers here wind up being the same numbers I would get if I were to multiply if I were to actually figure out the radicals in over here. So it's all awesome. It all works out beautifully. But negative 0.2828. That's negative 2 rad 2, and this here is actually negative 3 rad 2, and so on and so forth. It all works out beautifully. So my good friends, that is the story. That is the rotation of axis. It actually works. You could just type it. Again, I didn't do anything fancy here. I typed this in before I even before I even started doing it. Just when I saw the initial, there was this here, I just typed this in when I did the initial equation. I did the very initial equation here. Oops. Oops. Where was I? Yeah, this guy right here. I typed that in right there, and I got that picture that I just showed you. And now all the math that we did verified that we got that same information using matrices and transition matrices and all kind of cool stuff. So again, this is a wonderful, fabulous example of a practicality application of vector spaces. That is the end of chapter 4. Yay!